Another thing that we're going to use this for is to find probabilities for sample means. The requirements to be able to do this are that our original random variable x has to have a distribution. It may or may not be a normal distribution with a mean mu and a standard deviation sigma, and our samples of size n are all simple random samples. They all have to have the same probability of being selected. The result, if we meet these requirements, is that as the sample size increases, the distribution of the sample mean becomes more and more like a normal distribution. Here are the two formulas that we're going to use for our sampling distribution for our sample means. The first one is really easy because the mean of our sample means is just equal to the population mean. The second one is a little bit harder to remember. This is that the standard deviation of our sample means is our original standard deviation divided by the square root of our sample size. And another name for this is the standard error of the mean. Practical rules that we use for this: if we have samples of size n larger than 30, then we can pretty much count on our distribution of our sample means being approximately normal. We get closer to a normal distribution as our sample size becomes larger. The second one is that if our original population is normally distributed, then it doesn't matter what the sample size is. It can be smaller than 30, and still the sample means will be normally distributed. Here's an example. An elevator is designed to carry up to 3,000 pounds. Assume the population of weights of men is normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. How likely is it that a group of 16 men will exceed the safe capacity weight of the elevator? Figure this out. If we take 3,000 and divide by 16, that's 187.5 pounds. So what we need to do is find the probability that the mean weight for a random sample of 16 men is greater than 187.5. Because if it is, then the total weight of the 16 men will exceed the 3,000 pounds. That's the elevator's safe capacity. So we have a distribution of sample means that's a normal distribution because our original distribution of men's weights was a normal distribution. Our mean is 172. It's the same as the mean of our original distribution. And our standard deviation for this distribution is our original standard deviation of 29 divided by the square root of our sample size. So it's 29 divided by the square root of 16. It comes out to be 7.25. So now we just have a normal distribution with a mean of 172 and a standard deviation of 7.25. So we want to find the z-score for the 187.5. Then we're going to draw the picture of our normal distribution, and here's our sample mean of 187.5. The corresponding z-score of 2.14, and if we look this up in a table, the area to the left of that is 0.9927. We subtract that from 1 and we would get 0.0073. What that means is the probability that our 16 randomly selected men will have a mean weight greater than 187.5 pounds is 0.0073. So the probability that a random sample of 16 men will exceed the safe capacity of the elevator is only 0.73%. One important difference here is that we are finding the probability that the sample mean is greater than 187.5. That's much different than finding the probability that one man weighs more than 187.5 pounds. If we wanted to find that probability, we would use the mean and the original standard deviation of 29 pounds, and in that case we'd get a completely different answer of 0.2981. So the probability that one man weighs more than 187.5 pounds is almost 30%, where the probability that the sample mean for 16 men was more than 187.5 pounds was only 0.73%.